Hi everyone, thanks for coming along today. My name's Aaron Morton and today I'm going to talk about using large nodes in Cassandra, putting big data on a single node. A little bit about myself before we get started. I'm the co-founder and principal consultant at a company called The Last Pickle. We help clients deliver and improve Apache Cassandra-based solutions. I'm a committer on Apache Cassandra, and we have other members of staff who are MVPs with data stacks, and we're based in New Zealand and the USA. Just have to excuse me for 1 second. I reformatted my slides to fit on here, and I've just noticed they've cut something off, if you can excuse me. Sorry. So when I'm talking about large nodes, I'm talking about nodes that have more than 500 gigabytes of data on them. Now, a few years ago, I started saying this, don't put more than 500 gigs on the node, and it was initially about using EC2 nodes. And there are a number of reasons for that. It became more of a general discussion about how much data you could put on a node, and we've seen a number of changes in the last few years about this. But for now, let's say a large node is something that has more than 500 gigs of data on it. We could also think about a large node in terms of how many rows are stored on it. And in the past, we've seen issues where you have more than 1 billion rows on a particular node. So let's say as well, a large node could have more than 500 gigabytes of data, or it could have more than 1 billion rows stored on it. Sorry, my slides have reformatted badly.
You could go into revert to in the...
Ah, yes. Thank you. So prior to version 1.2, large nodes in Cassandra had operational and performance concerns. They were difficult to manage and they would have bad read latency. After version 1.2, these large nodes have fewer concerns, but they're still there, and we need to be aware of how Cassandra works so we can understand the problems. So what I'm going to do today is look at the issues we had before version 1.2 and look at some of the workarounds we used to use, so that when we look at the improvements that came into Cassandra after version 1.2, in version 2.0, and the things that are planned for version 2.1, we have an understanding of why those changes were made. And hopefully this will give you an incentive to use the more recent versions of Cassandra. To start with, let's look at memory management. Now, there are a number of structures in Cassandra that grow with the number of rows and the size of the data on each node. Bloom filters, as Jonathan discussed this morning, are held in memory, and they are the first point of call that we go to when we're doing a read. We look at the Bloom filter to determine if your row key may exist in your particular SS table. The size of that bloom filter depends on the number of rows that we assume are stored in the SS table, and the configuration setting on the column family called the bloom filter FP chance. Historically, this has been implemented as a two-dimensional array of longs, so each long is 8 bytes long, and this was held in the JVM memory. Now, the bloom filter FP chance has two different defaults depending on the compaction strategy that you're using. If you're using the size-tiered compaction strategy, the default is 0.01 or 1%. If you're using the level compaction strategy, the default is 0.10 or 10%. On this graph here, I'm showing how much memory we have to hold in the bloom filter for different numbers of millions of rows. If we look at the number 100 on the bottom, we've got 100 million rows, and when we're using the default bloom filter setting of 0.01, it's about 125 megabytes that we have to hold in memory. When we're using 0.10, it's about 65 megabytes. When we scale up to 1 billion rows, 1 billion keys stored on the node, at 0.01 for the bloom filter FP chance, we have to store about 1.2 gigabytes of bloom filter in memory. And for the 0.10 bloom filter FP chance, we store approximately 600 megabytes. Next piece of metadata of in-memory structure that we're concerned with is the compression metadata. When we compress your data, we do so in chunks. By default, each chunk is 64 kilobytes long, and the compression metadata stores where this chunk starts in the compressed data stream. So the size of the compression metadata depends on the size of the uncompressed data. We have more data on the node, we end up with more compression metadata. Just like the bloom filters, this was implemented in a two-dimensional array of longs that were allocated and held in the JVM. This graph here shows the size of the compression metadata when I'm compressing various numbers of gigabytes of data using the snappy compressor. For about a terabyte of data, 1,000 gigabytes, we have about 150 megabytes of compression metadata. And once we grow beyond that, the compression metadata gets significantly larger. And lastly, we have our index samples, which again Jonathan discussed this morning when he was talking about how we read from disk. We keep a sample of, by default, every 128th key from the index component on disk in memory. And this serves as a skip list and allows us to find a specific page of values in that file that may contain the row that you are trying to read from. So the size of this structure again depends on the number of rows that are stored on the node. When we have more rows, we'll have more entries in our index sample. This was implemented using an array of longs to store the offsets into the IndexedDB file, and a two-dimensional array of bytes that stored the row keys as well. So the size of this varied depending on how many rows we had and on the size of your keys. If you had large keys, they had to be held in memory. This graph here shows the overall size of index samples for millions of rows when the row key size is 25 bytes. So if we have 100 million rows, we have approximately 30 megabytes of index samples. And when we get to 1 billion rows, we have approximately 230 megabytes of index samples. and most of that is made up from holding your row key in memory. So these things are important to understand because the JVM is useful, but as Al was saying, there's no such thing as a free lunch. Larger heap sizes in the JVM, and by larger here we mean above the maximum default of 8 GB, take longer to GC. And a large working set, the amount of memory that we have to keep hold of that we cannot garbage collect, can result in more frequent and prolonged garbage collection. Because the garbage collectors can't free enough memory, and the thing that triggers them running is how much free memory there is. So they will run more frequently. Next issue that we deal with is bootstrapping. When a new node joins the ring, it takes ownership of token ranges. When it does that, it asks one replica for the token range to stream the data over to the node that's joining. And this is how it catches up on the data that was in the cluster before the node joined the ring. This sending process is throttled by a configuration setting called stream throughput outbound megabits per second, which defaults to about 25 megabytes per second. The reason that it's throttled is that at a very low level we ask the computer to move data off disk and put it onto the network, and that can go as fast as the network and the disk will allow it to happen. If we didn't throttle this, when a node was sending data to another node, it would saturate its network links and it would suffer worse latency when it was processing client requests. And one of the particular downsides of this implementation is that if you've got a replication factor of 3, each node will, when the node joins the cluster, it will only ask 3 other nodes to bootstrap data. Because it takes ownership of 3 token ranges, and if you have 30 nodes in your cluster, there will still only be 3 nodes that help a new node with bootstrapping. So because each of those has a maximum of 25 megabits per second sending speed, we've got a maximum rate of 75 megabits per second, and that is about 3/4 or 2/3 of the speed of a 1 gigabyte network. And there's also a problem here that generally with Cassandra, when you scale your cluster, we want the operations that Cassandra does to scale as well. So if you've been very successful and you've now got 30 nodes in your cluster, you would like to get a benefit from that. There's another process that we often use with clients where we move a node onto new hardware. This could be that we're moving a node onto a more powerful machine, we're moving it onto a machine in different networking infrastructure, or we're moving the node into a new physical data center somewhere else in the world. And when we do this, we shut the node down, we copy the data over to the new node and turn it back on, and Cassandra takes care of everything for us. The problem is, we're going to want to copy a lot of data, and if you're in a busy data center, you might get about 50 megabytes per second, and at that speed it takes about half an hour to move 100 gigabytes. And so if we have a large node with over 500 gig of data, it can take a while for this copy process to complete. Now, one of the most complicated things in Cassandra, from my perspective, is disk management. If we want to store over 500 gigabytes of data on the node, we're going to need multi-terabytes of storage on that node. One thing to keep in mind is that the performance of a disk degrades when it gets above about 75% capacity. So we've got a natural speed limit there. So we've got a couple of choices about how we lay out the disks. And remember, this is all issues we used to deal with. We could use RAID 0 and make one large volume. And if we lost a single disk in that volume, all the data on that node would become unavailable, and we would have to rebuild it. We could use RAID 10 and create a large volume with hardware redundancy. If we lose a single disk, we can repair that at the hardware level. But we need double the raw capacity, so there are additional costs. Or we could specify multiple data volumes to Cassandra. We mount each volume independently and tell Cassandra that there are 5 disks there. And in version 1.2, before version 1.2, sorry, Cassandra would just choose the disk with the most free space. And that could result in degraded performance because a disk would get multiple writes going to it at the same time. Additionally, a single disk failure would result in the node shutting down. The data would still be there, and you could go along and fix it, but it'd still shut the node down. The repair process is another concern when you've got a lot of data. 2 reasons we have repair. The first is to ensure that tombstones, our soft delete markers, are distributed around the cluster before compaction purges those off disk. The other reason is to ensure that our data is consistent on disk, and there are some reasons when that's desirable. It works by comparing the differences between nodes and then secondly streaming any differences that it detects. So that first process of comparing involves calculating the hash tree, the Merkle tree, which, as Jonathan said, involves reading all the rows in your table. And this is called a validation compaction. If you use no tool compaction stats while repair is running, you might see this happen. This runs through all the compaction mechanisms in Cassandra, and so it's throttled in the same way that we throttle compaction. There's a YAML setting called compaction throughput megabytes per second that defaults to 16. So if we need to repair a lot of data, it's going to be a throttled process, and that throttling is the same throttle that is used by normal compaction as well. So the time taken to do our repair grows as the size of the data on the node grows. Once we detect differences and we have to stream the results, we don't stream individual rows. We copy across ranges of rows because we only detect differences in ranges of rows. So if you have lots of very small rows, you will copy across lots of very small rows even if only one of them was out of sync. If you have some very large rows in the hundreds of megabytes, those large rows can get caught up in a repair process even if they're not out of sync because a smaller row nearby may be out of sync. This can result in multiple copies of your large rows sitting on disk, and you have to wait for compaction to catch up and free that space off disk. And again, the streaming process here is throttled by the stream throughput outbound megabits per second. Now, compaction is another fact of life in Cassandra. We have very, very fast writes because our storage engine writes new SS tables to disk. The downside of that is that we have to compact those, or we would end up with tens of thousands of files. The compaction requires space to write new SS tables. Size-tiered compaction groups the SS tables by size and assumes that there's no reduction in the size of the new file that it's going to create. So if it's compacting 100 gigabyte files, and it has 4 of them, it will need 400 gigabytes of free space. Now in theory, size-tiered compaction should have 50% free space on the disk. That was my phone. That's embarrassing. Now, in theory, size-tiered compaction requires 50% free space. And in practice though, I've seen systems run with less than 50% free space. It's not a desirable situation to keep for a long time though. The other choice is the level compaction strategy. As Jonathan was saying, this groups SS tables by level, and inside a level groups together the row fragments so that your row only appears in one SS table. This requires approximately 25% free space, so it can be more efficient. However, it uses approximately twice the disk I/O, and so should only be used when you're sure that you need it and you've got enough disk performance. So they're the issues that we had to address before 1.2. We'll look at some of the workarounds now, and this will help us understand why the changes were made in 2.0 and how we've still got some problems to solve when we have large nodes. The first workaround is we would reduce the size of the bloom filter by increasing the bloom filter FP chance from 0.01 to 0.1 on some column families. We saw this creates a dramatic reduction, approximately 50% reduction in the size of your bloom filters. The downside of this is that it may increase your read latency. As we get more bloom filter false positives that result in more disk I/O that is wasted. We can reduce the size of the compression metadata by increasing the size of the chunk length so that there are less chunks. And again, the downside of this is that it may increase read latency, because to read your small row now we have to decompress more data. And we can reduce the size of the index samples by increasing the index interval. Typically we might take this up to 512, an increase from the default at 100 that was 128. And again, this may increase read latency because now we have more data to read on disk in the index.db file than previously. We can also use a larger heap. And sometimes you might need to do this because you can't fix those other problems, or you've just got too much data. So I've run systems with a 12 gigabyte heap, sometimes up to 16, but we don't like to do it for too long. And when we're increasing the heap size, it's good to keep the new heap to something reasonable, which is about 1200 megs. When bootstrapping new nodes into the system, you can temporarily change the streaming throughput using node tool set stream throughput. You can disable it by setting it to 0, and so it will go as fast as it can. This is something you can do out of hours. So if you've got a downtime at night, you can increase the streaming throughput and try to get more work through at night. When you come in the next day and you've got more client requests, you can throttle it back again. If you're moving nodes to new hardware, we take a snapshot using node tool snapshot. We rsync that from the original node to the new one while the original node is still running. Then when we shut down the original node, we only have to rsync the changes onto the new node. And so there's significantly less data to move. For disk management, you didn't really have too many good choices. You could use RAID 0 and perhaps over-provision, expecting that there could be some failure. So you might have a node that's just sitting there, not actually in use, so that if one fails, you can very quickly move to a new one. A lot of people would use RAID 10 because operations teams are happy with RAID 10 and accept the additional costs. I wouldn't recommend using multiple data volumes prior to version 1.2 of Cassandra. For repair, my personal opinion with repair is that it's worth the effort to make it work. If you've got a lot of data, it might be a lot of effort. And so you could perhaps only use it on tables that have deletes, and instead rely on the consistency level to ensure that your data is replicated. Another option is you can do more frequent repairs on smaller token ranges. So rather than repair an entire table, you can, if you know how to use JMX, go and repair just portions of a table at a time. Compaction, you need to over-provision your disks to make sure you've got enough free space. This is a problem that will never go away. You will need to have lots of free space on your disks. If you're in a situation where you've run out of disk space and compaction's not working, you can reduce the min compaction threshold and the max compaction threshold to reduce the number of SS tables that are included in each compaction, and therefore reduce the amount of free space needed. The downside of this is that compaction will be more frequent, and that may result in increased read latency as your disk I/O gets eaten up. And you can use level compaction where appropriate. I wouldn't use level compaction until at least version 1.2. It had some issues. And if you're going to use it, you need to make sure that you have done some testing and you've got the appropriate disk I/O infrastructure in place. You might use it on perhaps one column family that receives, one table, that receives a lot of overwrites, and not on the others. So we've got an understanding now of how Cassandra works and how it doesn't work as well sometimes with lots of data, and what we can do to help it. From version 1.2 and 2.0, there are a number of changes that solve fully or partially all of these problems. And there are things coming in version 2.1 that continue to improve the situation. The biggest changes that happened in 1.2 was that these data structures were moved off the JVM heap. The bloom filters and compression metadata were moved off in 1.2, and in 2.0 the index samples were moved off the heap. Now they still take up memory on your machine, but they're no longer the concern of the JVM garbage collector, which is good because the JVM garbage collector will stop your Cassandra server running while it does some garbage collection. And we want to minimize that time. So because it's still taking up memory, all those tricks we saw about how to reduce the size of the bloom filter, the index samples, and the compression metadata still apply. Bootstrapping was improved by adding virtual nodes. And this was one of the two stated reasons for adding virtual nodes. The other was to make it easier to grow your cluster. Previously, the easiest way to grow was to double the number of nodes. And people were happy to go from 3 to 6, maybe happy to go from 6 to 12. Not everyone was happy to have to go from 12 to 24. So vNodes help us because we can now easily grow 1 or 2 nodes at a time. What the virtual nodes do is they change it so that each node now has 256 token ranges that it owns, whereas previously it only owned 1. So when the node joins the cluster, it takes ownership of 256 token ranges. and it asks one replica from each of those token ranges to send it data. So now we have up to 256 different nodes in the cluster sending data. If they each do a small amount of the work and send a small amount of network, we can easily saturate the receiving node and we can bootstrap faster. And importantly, as your Cassandra cluster grows, this process scales. There are some good disk layer improvements. We now have, under the umbrella of an idea called JBOD, just a box of disks, better support for having multiple data directories specified in configuration. Cassandra will choose the data volume that has the most space that is also not being written to by another process. So previously we would just find the data volume that had the most space, and so we could have 3 SS tables being written at the same time to a particular disk. Now, if we're writing 3 SS tables at the same time, they will be distributed across 3 disks. And so we're taking advantage of the parallel disk I/O. We also have a disk failure policy. This tells Cassandra what to do when we detect a disk I/O error on one of our volumes. It has 3 settings. The ignore setting tells Cassandra to ignore it, but it doesn't actually ignore it, it just lets the exception shut down the server. This is how Cassandra used to work prior to this setting. The stop setting tells Cassandra when you detect a disk I/O error, you should log it to the system log, add it to the JMX information, including a notification section on JMX, and disable the APIs, the binary API and the thrift API, and disable gossip, so that essentially now the node has been taken out of the cluster. Now an operator can come along and inspect this node and understand what the problem is. They can then take the appropriate action, which might be restarting the node or replacing the disk. The best effort setting is handy but should be used with caution. It tells Cassandra that when it detects a disk error, it should just stop using that disk but keep on processing reads and writes. So again, it will put this into the system log, it will make it available via JMX, including JMX notifications, and it will act as if nothing happened. But of course, if you had 4 disks and you lost one, 25% of the data on that node has now disappeared. If you're using Cassandra in a strongly consistent mode, with quorum and quorum for reads and writes, this won't be an issue. If you're using Cassandra in an eventually consistent mode, perhaps using CL1, you now potentially will get stale data. And stale data always includes the idea of no data, because initially there is no data. Jonathan touched on these next 2 improvements in his morning talk, so I'll talk about them briefly. Repair, it's been scheduled to go into 2.1 to have a dramatic improvement. If you do a full repair on Monday, and then you do another repair on Friday, we will now only repair the difference between Monday and Friday, which will have a dramatic improvement in the way that repair works from an operations point of view. Compaction may compact these things. Compaction is impacted by this, but we don't think is going to have any major operational concerns. Now, when compaction does its work and it takes 4 files and merges them into one, As Jonathan said this morning, we previously assumed that if each of those 4 files had 1 million rows, the output file would have 4 million rows. And so the bloom filter was then allocated appropriately to hold 4 million rows. The work in Cassandra 5906 to use hyperlog makes it easier for us to allocate the appropriate bloom filter size. And so this should also see a reduction in memory. And that's all I have for today. Are there any questions?